undergoing simple harmonic motion. It's basically just a back and forth motion. So it's going to change between potential energy and kinetic energy. And the kinetic energy is the formula that we kind of know.
Right. Can you move that chair there? Move it on the
1/2 times mass times the velocity. Square. Good. Yeah, square. And we have a function describing the velocity at any given point. So finding a formula for the kinetic energy in simple harmonic motion, it doesn't really require that much. We just have to then just write 1/2 times v squared. Then I just have to take this function here. Oh, that was badly written. Omega t and square that. So I can clean this up. So that's 1/2 times mass times omega squared times maximum displacement squared times this cosine omega t plus the phase difference and square. So when we square a cosine function, we have cosine squared and then the angle. All right, so that formula you'll not see in the formula booklet. That one that will not be in the formula booklet. A better one will be in the formula booklet, but that one takes some time to derive. So but this is one general expression for the kinetic energy. If you know maximum displacement, you know omega, and you know the time and the phase difference. But before I continue with kinetic energy, I can use this formula to say something about the total energy. Because remember from yesterday that one way of finding the total energy is two options. Either find the maximum potential energy or the maximum kinetic energy. So here we have a formula for the kinetic energy, which our mass is constant, omega is constant, and the displacement that is the same throughout. Only term is this term here that changes with time. And the maximum value of this term here is 1. So basically the formula for total energy, all right, T, I can just write that that's the kinetic energy. I can just write brackets here, just indicating that's the maximum value of the kinetic energy. So then the total energy of an object undergoing simple harmonic motion is 1/2 times mass times omega squared times the maximum displacement squared. That is the formula describing the total energy. But what they do now in the book, and they go back in the book to talk about the kinetic energy, because the kinetic energy continued. I'm not sure if I should I can show the entire part, but in math, have you seen this one here? Cosine to x squared plus sine to x squared. What's that equal to? 1. Okay, you have seen it. Good. Good. I take a look at this one here. So I go from this point here. I write, let's see if you understand what's happening here. 1/2 times the mass omega squared x0 squared. I write brackets, and I write this in terms of minus sine squared omega t plus the phase difference. Now I regret using the phase difference because it just makes a lot of writing. Does anyone follow what has happened here?
Yeah, but why did you do it?
Yeah, that's a good question. Why did I do it? That's second part. But you understand what has happened here. So basically, I had something with cosine squared. I wanted to write it in terms of sine. So cosine squared to x is 1 minus sine to x squared. That's what I did. Now,
Just before you explain that, could you just repeat what you said about the fact that there being a maximum, like the maximum kinetic energy will tell you or like you said something about.
yeah,
what
so
was it?
when I derive the formula for the
Yeah.
total energy,
Yeah.
right? That's equal to the maximum kinetic energy
Or
the maximum potential energy.
Okay.
And since I have a formula now for the kinetic energy, I use that.
Yeah. Okay.
I don't have any information about the potential energy.
Yeah.
All right. Then I start now multiplying this one into my equation. So now I can write this as 1/2 times mass times omega squared times x0 squared times 1. That's just leave it there. And then I have 1/2 times mass omega squared x0 squared times sine squared to omega plus there. I just multiply that into it. Now comes the y part. Because if I look at this one here, x0 squared times sine omega t plus the phase difference squared. If you compare it to this one here is basically just this one squared. So basically this here is just x. The position
Squared.
Yeah, x squared. Good. Thank you. Right. So x is not a number, x is the position of the object at one given point. So that means that I can write this thing here as 1/2 m omega squared x0 squared minus 1/2 m omega squared x squared, where x is the position of the object at one specific point. And I can factor out the common factors. So I can write this as 1/2 times mass times omega squared x0 squared minus x squared. And I believe this one is in the data booklet.
Can you leave this on the whiteboard so you can use the
Yeah,
next
it's
physics
just
class?
Do we need to know how to derive?
No. But that's the fun part, you know? That's the fun part. But with this formula, a new thing comes up. Because what is kinetic energy? Kinetic energy is 1/2 times the mass times v squared. That means that this part here, that's equal to v squared.
Why am I so annoyed?
So that's equal to v squared. So suddenly we get a new formula. That v is basically just the square root of this here. So that gives us plus minus omega square root of x0 squared x squared. So everything is done. You start off with a kinetic energy. You can use that to find a formula for the total energy, and you can use that to find the formula for a new formula for the velocity, where you don't need time, you just need to know the position of the objects.
You said that. Oh, never mind.
I say a lot of things. Yes.
Why is
And
it-
yeah.
Why is it? Never mind. Never mind. I understand.
If I know the total energy and I know the kinetic energy, how do I find the potential energy?
Find the difference.
To find the difference. So the potential energy is the total energy minus the kinetic energy. Meaning I will take this expression here. I will take this expression here minus this expression
What do you do
Here.
with the same equation? You
Here.
just get 1/2 mv squared.
there. So this minus this one, I'm not going to do it, I'm just going to write the answer to that. That's going to be 1/2 m omega squared times x squared. Because if I take this minus this one, these two cancel each other out, and this becomes what's left. Try for yourself. Remember to include.
I didn't find. I don't think it is in the formula booklet, or is it?
The potential energy? Yeah.
Because I didn't find it in the when I checked. Like, alright.
Yeah, is there. So basically, you just need to be able to use them. You won't be expected to derive them, but some ideas is useful. That's for the standard level part, right? Understanding that how to find the total energy, maximum kinetic or maximum potential. If you know the total and you know the kinetic, you can find the potential. If you know the total and you know the potential, you can find the kinetic. So it's very mathematical. Some people, students like that. More math, easier it becomes because you just have the formulas. So this works in either way. These formulas work no matter what the situation is. If it's elastic potential energy or gravitational potential energy, those formulas work. Alright, so now you have 10 more minutes to continue with the problems. Look very...
We'll end up finding the same expression after doing tons of math. That can be kind of
I
annoying.
only agree with you. I don't know. And it's on the